and I have the honor of being the session chair. And joining me as the session co-chair is Dr. Zishan Ali. Over the next few hours, we will have the privilege of delving into exciting discussions, thought-provoking presentations, and valuable insights shared by our esteemed speakers. Without further ado, let us embark on this collaborative journey of knowledge, exchange, exploration. On behalf of the organizing committee, I sincerely thank you for joining us in this technical session, and I hope you find it informative and inspiring. As the session chair, I am excited to witness the diverse range of cutting edge research being presented today. I kindly request all speakers to keep their presentation concise and engaging, allowing for ample time for discussion. Please feel free to raise any questions or concerns during the question answer segment, and we will do our best to address them. Now, I would like to invite our first presenter, Dr. Asif Khan. He is from GIKI Topi, Pakistan. The topic of his presentation is delamination localization in smart laminated composites, a transition from conventional to contemporary approaches. Over to Dr. Asif Khan.
Thank you so much, sir. So is my screen visible?
Your screen is visible, but your presentation is not shared yet.
Okay, I think on my screen it shows that it is shared, but let me share again, maybe stop sharing and I will share. So can you see the screen presentation now?
Not yet.
But in my case, it shows it is shared.
It is still black. Okay, now you can start your presentation.
So is it visible now, right?
Yeah. Okay.
Okay, so and also maybe there was some issue in the slide movement. So can you confirm that the slide is changing? Is my slide changing? Can somebody confirm? For example, the next slide.
Yes.
Okay, thank you. Then I will start. Okay. So thank you so much for the introduction. So my name is Dr. Asif Khan, and I'm going to talk on the delamination localization in laminated composites, where I will be discussing the transition from the conventional approaches to the new modern era contemporary approaches. So as all of us are aware as domain experts, laminated composites are continuously replacing conventional lightweight metallic isotropic materials in various industries. For example, the major consumptions is made by these aerospace and aircraft industries, robotics, for example, sports, protective gears, automotive transportation, nautical application, and defense sectors and others. For the area-specific application, for example, renewable energy in the form of wind turbines is one of the major consumer of laminated composite. Similarly, civil infrastructures are now shifting towards recyclable laminated composites and composite structures. Automotive industry is another larger consumer of these materials. And as we are well aware that these days, the modern aircrafts are manufactured for more than 50% of the laminated composites, which basically shows that these materials are very important, and with the passage of time, their importance is growing. Looking at the market size of laminated composites, so as projected by this specific industry, up to 2030, the market size of laminated composite is going to be 163 billion US dollars, which is a huge market. And also, if we look at the trend of increase, it doesn't appear to be a linear one, but in some places it looked like a quadratic increase, in other places it looked like a linear. So it means there is a huge market for these laminated composites. However, as domain experts, we know that these laminated composites are not isotropic. They are highly heterogeneous in nature. To be very specific, they are orthotropic in nature. which means that compared to isotropic material, their failure or the nature of damage in these materials is also going to be much more complex. So some of the commonly occurring damages in laminated composites are, for example, delamination, voids, fiber breakage, cracks in the matrix part of the laminated composites, the disbond between the matrix and the fiber material. And if we are talking on the sandwich structure, then the core disbond, the splicing of the core are some of the common defects. Then the common sources of defects, there are two common sources of defect. One is these defects can be induced when we are manufacturing any laminated composite structure or part or component. The second is they can be induced because of the in-service loading conditions. And delamination is basically one of the major mode of failure in laminated composites, which basically starts from obviously the micro cracks and ultimately end up in the form of separation of layers, which we known as delamination. And this can ultimately lead to the catastrophic failure of the structure. So this is one of the serious flaw or defect in the laminated composites. There are various physical parameters or various physical factors that basically affect the initiation and onset of delamination in laminated composites. For example, it can be initiated during even the manufacturing process because of the high residual stresses. It can be induced by the environmental effects, for example, thermal stresses. During the machining process, more specifically a drilling process, can easily induce the separation of layers or delamination in laminated composites. Because of the specific geometric configuration, because we have laminated composite are composed of layered structure, so we have high free edge stresses, and if the shape, the geometric configuration is in a specific order, we may face the issue of high free edge stresses that may ultimately lead to the initiation and propagation of delamination damage. And obviously in service during the operation, because of the loads, more specifically low velocity impact and high velocity impact can also result in delamination in the laminated composites. Because as I mentioned in the beginning of this presentation, laminated composites are very, very important in so many areas of applications. So, and they are also vulnerable to various types of defects. So their non-destructive evaluation and testing is also very important. If we look at the market size of the non-destructive evaluation and testing technologies, by 2027, it is projected to be around maybe 3.5 billion market only for the technology that can assess the health condition of the laminated composites. So the various commonly employed and well-established non-destructive evaluation and testing techniques for laminated composites are, for example, xerography, acoustic emission, radiographic inspection, ultrasonic inspection, thermography, and on a larger scale, for example, the very basic one is the visual test and acousticography and vibration-based methods. However, most of the non-destructive evaluation are suffered from some limitations. For example, these techniques, the well-established techniques, are most of them are basically for the local assessment. For example, we can only employ these acoustic instruments or these radiographic or other non-destructive evaluation instruments and techniques on a certain part of the structure, basically, which we are going to inspect. Another issue is in order to implement all these techniques, the structure must be put off the service. So it means these techniques are not suitable for in situ, in service structural health monitoring and non-destructive evaluation and testing. Similarly, if we want to implement these techniques for large and complex structures, such as, for example, aircrafts, so then again, our aerospace structures, then still, because we cannot put them off the service during their operation, so they are even not feasible for those. We know about the structural vibration. This is more readily available. And more technically, we can speak, this is passively available because of the, for example, the engine firing frequency. And as a result, we can employ this one for the structural health assessment, for the structural health monitoring and non-destructive evaluation and testing. So that's why our research group have specifically focused on the vibration-based non-destructive evaluation and testing and structural health monitoring of laminated composites. Now, in order to realize the importance of vibration-based methods for health assessment of laminated composites, here is, although this is not very up to date, but still it will just give you a general idea. Up till 2015, this is the amount of or the volume of the literature or the research work done on the laminate vibration-based condition monitoring of laminated composites. And as we can see from the trend, that these are very powerful techniques for the health assessment of laminated composites. Then in the vibration-based methods for the health assessment or condition monitoring, we can divide them into three major categories. The first one is guided wave-based method. Second one is acoustic emission-based method. And the third one is structural vibration-based method. From the structural vibration, I specifically means low frequency structural vibration within the range of 0 to 1000 hertz at max, basically. Okay, if we talk about the guided wave-based methods, then the overall technique or the overall methodology is to induce a high frequency signal into the structure with the help of a piezoelectric patch. And then that is going to propagate inside the material as elastic wave. And another transducer or receiver or piezoelectric patch receive that in the as a sensor. And we basically analyze this signal for the health condition in the path between this actuator and sensors. But the issue with this kind of approach is because the excitation signal that is provided by the actuator is of high frequency. So in order to keep the useful information of the signal, we must store the data at very high rate. So it means this is not very convenient for real-time continuous structure health monitoring, because for a very short amount of time, we have to store a very large amount of data, and then processing that data would be another issue at a high rate. Another method is acoustic emission, which basically refer to whenever there occurs some kind of damage, it basically release a stress wave, And if we can capture that stress wave through this acoustic emission sensors, then we can say something about this one. But the limitation of this method is there should be some damage event. And even if that damage event is not propagating, then capturing that damage event would be difficult. Another limitation is if there is surrounding noise, then separating the acoustic event from the surrounding noise is a really difficult task. The third one is structural vibration. One of the power of the structural vibration is this is passively available to us just because of the operation of the structure. This has been successfully implemented for the detection of delamination. In other words, we can say the global assessment that there is damage, there is no damage. And the most commonly used indicators from the structural vibration are the natural frequency and modal damping, which can basically help us identify the presence of damage or there is no presence of damage. However, employing the structural vibration for the localization of damage is one of the challenging tasks for the research community, that we can assess the structural vibration, low frequency structural vibration for the damage detection, but it cannot be correlated with high accuracy rate with the location of the damage. Coming to the low frequency structural vibration in general, as vibration engineers, we know that high frequency modes basically capture the local responses or the localization information of the damage. And lower frequency modes of vibration basically capture the global response, means the overall structure response characteristic or the deformation pattern of the structure. But in generally for low frequency, we only have access to the low frequency modes. And also, if we want to excite the higher modes of vibration, we need more energy. And the analysis may easily shift in the higher modes from linear to non-linear analysis, which are much more difficult to handle. So these are some of the limitations associated with structural vibration. Then some of the conventional approaches used for the vibration-based methods are, for example, the first one we called as physics-based approach, and the second one we call as statistical-based approach. The other contemporary approaches are the modern tools are machine learning, deep learning, and transfer learning. I will try to quickly cover all these aspects. So physics-based tracking means we just capture the signal from the structure with the help of a sensor, and then we try to look for some damage indication. For example, we know that whenever there occur a delamination damage, it causes the loss of stiffness in the structure. Loss of stiffness in the structure means the loss of structural, reduction in the natural vibrating frequency of the structure. So keeping track of this kind of indication, we can say on a single signal, we can decide whether there is something going on in terms of the structural integrity or not. And again, we can also do the same thing for different modes, for example, for the bending mode and the twisting mode, and which mode is more sensitive to the shift of the frequency as a result of the presence of defect. Similarly, frequency response function or FRF, commonly known as FRF, We can also look for the shift of the natural frequency as a result of the damage in the structure. And we can, from that one, we can look for some physical parameter associated with the initiation of damage. Similarly, for example, the damping capacity or the damping coefficient, we can, which is difficult to measure in any dynamic testing. But if we can keep track of that one, we can look some specific trend for the presence of damage and its severity, basically. Some other commonly employed approaches are, for example, extracting some damage index based on the mode shape measurement of the structure. And based on that damage index, we can say for the damage mode, we are going to observe some specific spikes in that damage index. Same, for example, the model analysis, the mode shape measurement experimental, and based on that one, we can basically come up with some damage index, which will show that there is a damage as a specific location in the structure. Again, we can also work on some statistical features, and based on that statistical features, we can come up with some visual-based method, which will show us if the cluster is occupying this specific space in my plot, a two-dimensional plot, then that's the healthy state. If the cluster location gets changed, then that's basically a different damage state of the structure. However, these conventional approaches suffer from some limitation. For example, they are good enough for the delamination detection, which means for the global assessment of damage, but they are not good enough for the localization of the damage. And although the model analysis or the mode shape measurement has been successfully employed for the damage localization, but as field experts, we know that measuring the mode shape experimentally for complex structure is even simply not possible. So, which basically give us the chance, if we can analyze the structural vibration with artificial intelligence, which are really intelligent in processing different complex pattern in the signals, we may extract both the local and global information from the structural vibration. Because of the time limitation, I will skip some of the slides. For example, this general discussion, the difference between machine learning and deep learning, then what is transfer learning, how it works. If needed, we can discuss this later in the discussion part or through email maybe. Again, I will discuss. Okay. Then one of the contemporary approach is machine learning approach. And what we do in this one, we basically try to get the signal from the structure in different health condition. We try to come up with an intelligent approach of transforming those signatures, vibration signature, into a discriminative feature space. And we try to classify that, discriminate or analyze that discriminative feature space with the help of artificial intelligence. And artificial intelligence can give us the result in the form of these kinds of confusion metrics. And we can associate or correlate the results of those confusion metrics with the different health states of the physical structure, and we can try to get physical insight in the structure. So, for example, in this specific work that we have published, we have used the excitation signal and the response signal to construct that discriminative feature space, and subsequently analyze that through machine learning models. We were even able to train the model and make prediction for even totally new kind of damage in the structure, and we were able to get physically consistent predicted labels for totally new type of damages that were not being used during the training process of the machine learning model. Similarly, because in practical situation, we may have access to the response signal because that is easily measurable with the help of any installed sensor. But what is the source of excitation for that response? It is simply not possible. So what we do, is it possible to classify or find out the damage and its location information just from the structural vibration? So for that one, we implemented a deep learning strategy, and we transformed these vibration signature to spectral images through simply short time fast Fourier transform. And then we employed convolutional neural network to classify those images. And again, we were able to obtain a 90.1% accuracy with a very good looking confusion metrics. And this confusion metrics were very consistent with the actual physics of the problem for different damage scenarios. Again, the pre-trained convolutional neural network was able to make physically consistent results with 100% correct prediction capability, even for the unseen cases of the damages. Then we also analyzed, for example, different location of the damages. And based on the predictions from the deep learning model, we were able to extract and look into very good insights. For example, any damage that occurs at the inside, delamination damage. For example, all the four boundaries are bounded to the structure. This is inner damage. So we observed, based on the artificial intelligence, that is less severe compared to any damage that is occurring on the edge side and one of the side is open, for example, to the edge side, then that is going to be more severe in terms of response characteristic compared to this inner damage. Similarly, any damage in the configuration of cantilever plate was less severe compared to the same amount of damage, but near the free end of the cantilever configuration of the plate. And we were able to get these kinds of insights simply from the artificial intelligence and the associated confusion matrix. Again, we often know that we have access to only limited data from the actual measurements. So we also try to analyze that limited data in the framework of transfer learning. The idea is to just use off-the-shelf pre-trained model and retrain this one for a new data set, or try to use this for extracting feature from a new data set. So this is the result when we did not apply this transfer learning, and we see the performance is not very good. But when we applied this transfer learning strategy, we were able, for example, to get the accuracy up to 98, 95, and 100%. For the simulation data, the results are the first two categories were not well good. But when we looked back to the physics of the problem, we observed that the major loss of accuracy was happening in this specific portion. And when we looked at the physics, then this L1 damage was very close in response, very small amount of damage, which was almost very similar to the healthy case. So we were able even to find out the physical cause for this confusion by the machine learning model. Again, as I mentioned, in experimental cases, we have access to very small amount of data. So can we come up with some technique to artificially augment that data? So for that one, we also applied another technique. We basically excited the structure with a very broadband excitation signal, commonly known as chirp excitation, and we obtained the corresponding responses. We use that excitation signal and the response signal in a back inverse kinematics, and we try to develop a black box model of this model system. Then we excite the black box model, not the physical experimental setup, with different excitation. And this way we were able to augment the data and validate that augmented data as well. So this is the result when the data was not augmented on 45 signals. And we were able to augment that 45 signals of the physical measurement to 4,545 data point or measurements basically. And you can clearly see the effect of that one. The 80% has increased to 98% accuracy, 86 was increased to 99, and 100% was remained unaffected basically. So concluding basically the presentation, the ideal case of delamination detection and localization is from physical parameters. And the reason is in physical parameter means we just can analyze the health condition just from a single signal. For example, if we can extract the natural frequency information from that signal, we can associate the shift of natural frequency with the damage. But associating that physical parameter with the location of the damage is simply not possible from structural vibration. Among the vibration-based method for delamination, structural vibration is ideal because this is more passively available to us during in-service. For example, as I mentioned, the engine firing frequency always induce some vibration in the structure without any additional sources of excitation, and we can use that vibration for the health assessment. However, extracting the health-related information, the local and global one from that structural vibration is most of the time difficult, but as we quickly saw, machine learning, deep learning, and transfer learning methods can help us infer that vibration signature for both global and local informations. There are certain limitations for the artificial intelligence, and more specifically for the local frequencies, local structural vibration, but we are still working on that one. Just because of the time limitation, there are also some challenges, but I will skip these ones, and also some future scope. So if needed, we can discuss through email or during the question and answer session. So thank you so much. And if you have any questions, you are more than welcome.
Thank you, Dr. Now the house is open for question answer session. If anyone have any question, he can ask from the Dr. Asif Khan. I think at the moment there is no question. Thank you very much, Dr. Asif Khan, for this valuable presentation. Now, I would like to invite our next speaker, who's Mr. Dr. Abdul Shakur from University of Engineering and Technology, Peshawar, Pakistan. He will give presentation on the topic of development of novel biopolymers composite for structural application. And Dr. Abdul Shakur.
you. Thank you. Thank you, Dr. Saab. Is my voice is audible?
Yes, doctor. I can hear you.
Yeah, let me share the screen. Yes, can you see my screen?
Yes.
Is this loud and clear?
Yes, doctor, it's clear. You may start now.
Okay. Okay. Thank you, NTU, thank you ICPC for inviting me this international conference on composites. It's been a pleasure to be here. Today I'm going to talk about my involvement with the development of this novel biopolymer composite for structural application. I've been listening this since yesterday. And it was really interesting, some interesting talks we have been listening, and all that was focused on the theme of the project, the conference. I'm really, let me introduce myself first. I'm professor in Department of Mechanical Engineering, UET Peshawar here. Being Director ORIC and working as the Associate Professor as well. I worked as Associate Professor. I done my PhD back in 2013 from Loughborough University, and currently I'm an Associate Fellow of the Higher Education Academy of UK and Associate Member of the Institute of Mechanical Engineering UK, and a Fellow of Institute of IAP Pakistan. Yes, we have seen this historical evolution of the engineering material and they have a very close interaction with the human civilization and the society. As the civilization grows, at each stage of this human civilization, they have been involved with some sort of the materials. So if we start from the Stone Age until now, the silicon and the graphene age. So at each stage of their human civilization, the humans are being in touch with some sort of material. And if I say that the development of material is going side by side as the human civilization grows, and the level of comfort we see around and our daily life is all because of material we see around. There are different type of material we see around, and then we have seen a global production of the plastic, because when we goes into the plastic age, so we have really seen some good the global production, and based on that one, some sort of the let's say the global production there. But the problems here that we have a worldwide production, there is the waste is also associated that is being generated with this global production of the plastics. There are some waste which is being discarded. There are some waste which is being incinerated. Yesterday, we've been talking to one of the keynote speaker, and he was talking about this one, this all was recycled. And if I quote his figure, that only 10% of the material waste that is being recycled. Yes, this is no doubt. And that's where the problem lies, that we have been generated 100% and only 10% of that material is being recycled. So then, because of that one, as a result, we have seen this pollution of ocean pollution and the ground pollution and all different type of pollution. And because of that one, we see these kind of campaign that we have said no to plastics. But it's really a wise thing. Yes, somehow you can say it, but in my personal view, it's not like you have to give some sort of alternatives to the society for their daily life application and daily life use in order to at the same affordability and the same economic with the same technical competencies and technical justification of that material, unless and until we will not be able to stop it. And then but there is ray of hope that we are talking about sustainability, and we are talking about a material that can solve this problem up to somehow. And we have seen a different type of material, like we have seen the biodegradable material, we talk about the biocomposite, we talk about sustainable material, we talk about the green material, bio-based, and all these because this sustainability will be a driving force for the next generation and decades for when we develop a products, material, or any process. And there are some, like we can see some niche words of like different. They are the same, but they are already different. There are material which are graded as a biodegradable, but they are simply not biodegradable. There are compostable material, there are renewable material, there are biopolymer. So there are end of life is concerned and there are start of the life is concerned. So we talk about the natural fiber reinforced synthetic polymer, which are non-biodegradable, the biopolymer reinforced by natural fibers, or the biopolymer reinforced by synthetic fiber. So the polymer, is this the polymer biodegradability is an advantage? Because the earlier plastics were criticized because in the start, the human civilization were using the plastics and they were all the natural plastics. And their plastics were criticized for their short lifetime performance. And the polymer technologies usually seeks to improve the lifetime of the plastic, whether there's thermal oxidative or ultraviolet degradation of the material or mechanical degradation of the material. They were looking to improve this one. So the poor durability was one of the reasons from switching to natural to synthetic polymer and synthetic rubber material. We see a different application of these biopolymers. We see these agriculture mulching film. We see this packaging, electronic industry, automotive industry, textile thinking. But most of the application of the biopolymers are limited to only the short product life cycle. And that is most of them are packaging or agriculture mulching film. There are different type of the innovation they are taking place, which to use these materials in electronic industry, automotive industry, textile thinking, but still we need to make these materials socially acceptable, technically competent, and economically viable. And that is where the challenge lies for these materials. Because these biopolymers have some sort of limitation in terms of the poor processing problem, because there is a very narrow margin of windows for processing. They have a very poor mechanical properties. And when we compare that to the synthetic polymers, and some of them are poor thermal stability. So we need to have a holistic approach to solve these issues by developing a composite technology for widespread application of the biopolymer and to make them mainstream into the structural application of the material. In order to develop the biocomposites reinforced with natural fiber and mineral filler, this was one of the objectives that with improved mechanical properties. So we developed this composites with PLA, one of the major biopolymer that is being used commercially. There are different grades of PLA. So, but what I'm talking about the first grade of PLA, the generation 1, which was extremely brittle material at that time. And the wood composites, we developed the wood composite along with the copolymer because there was some issue in the viscosity of the material because of the heavy viscosity of the polymer, it wouldn't able to inject or to penetrate into the wood narrow channel. And because of that one, the composite was as a whole having some sort of the toughness issue. And to solve that one, we developed a copolymer with that one, and it was targeted the viscosity of the PLA, and that has been sorted out. So we have developed thermally, there was no significant change was observed in terms of the PLA wood composites, but we have seen a very significant improvement in the mechanical profile of the material, and there was significant improvement in stiffness and the modulus of that material, which was also compared with the modulus with the modeling, and that was very that have very correlation with each other. Viscoelastic point of view, say that was not that much significant properties was being observed because there was the load, the damping capability of the material was not being properly improved. And then we were looking to improve some hybrid composite of the biocomposite material to develop the PLA, hemp, and hemp fiber, natural fiber, and then the ENR that. And because of that one, there was some ductility or just like the toughness was slightly improved with that one. And based on that one, we also seen some sort of the increase in the thermal, like the heat distortion temperature, and improve the damping capability of the material. So this was one of the improvement that has been significant, and that was published. Then, in terms of the natural mineral filler, that one of the talc is one of the abundantly available in Pakistan and around the world. So the talc was used as a mineral filler in it to improve the mechanical profile of the material. So two different type of talc fillers were being used. One 1.9 micron micrometers, and the other one was 2.2 particle size. And significantly, we have observed that there is a huge significant thermal properties has been improved with the mechanical profile has also been contributed by that one. And the thermal properties was also being improved by increasing the crystallinity of the material from 2% to around 27% of the crystallinity has been improved with the fraction of the the talc filler is increased from 0% to 30% of the volume fraction. So this was one of the significant improvement that has been observed. The viscoelastic nature of the material is also being improved significantly, and because of that one, the from industrial application point of view, the heat distortion temperature of the PLA was improved, and that was being applied in the commercial products as well. So this was, and mechanically, there was a huge significant improvement in the mechanical profile of the material. And that was complemented by the viscoelastic nature of the material as well. So they all each complemented each other. And also the damping capability of the material is also being improved. The biopolymer improved with the talc incorporation in the materials, in the polymer. This was observed, and 0.9 point, like the square, the R square value was recorded at 0.98. So that was a significant correlation between the experimental and the theoretical result of the material. We were not able to, or we were not only limited to this one, we are looking to some sort of the Loughborough University, UK. We were doing some sort of the textile working on that one, and to do some sort of sustainable tensile thinking. So we were using, because they were interested in to do some sort of interior decoration textile thinking of that one. So we were having this expertise to develop this PLA. So we provided the expertise on the PLA fibers, and it will also use the flax fiber as well. So this is a kind of wood PLA, and this is the flax PLA fibers, and this was all been, and lasers technology has been used to cut down these kind of material, these flax fibers, and the interior decoration were being some sort of just like exposure in order to improve this design thinking, localism, using local resources, technology, and emotional durability for purpose as well. So this was one of the bio-interior design that was being developed with the PLA, the flax fiber. So because generally there are some issues with the biocomposites material, because and that is affecting the uptake of these biocomposites material. One of the main issues, because there are very limited people who manufacture, who work on these kind of to make it more sustainable. So the availability and the cost is one of the issues with that one. It is very difficulty because when we are talking, so there is a school of thought that we're talking about the food crops as well. So there is also another issue with that one. It is have difficulty and very narrow margin of processing as well. Because of that one, it has a poor barriers and toughness properties, and there is no viable end-of-life disposable except for home composting of the PLA. Particularly, I'm talking about. I'm not talking about because the PLA, the people is branding them as a biodegradable material, but that's not biodegradable. It is it's compostable material, and it needs to be home composting. And because of that one, the people are mixing this material with the degradable material, and because of this issue, not the degradation properly take place, not the home composting taking place, and that's why the people get disappointed that it is not degradable. There are some ways forward. We can use plant biomass instead of food grade feedstock. We can use additive composite and to exploit this composite technology to improve the properties of these material. We can have a focus on application that offer main advantage, not particularly just to develop a biocomposite, but we need to focus and target some sort of main or advantageous oriented application of these materials. We need to discourage this application which can interfere with the recycling of the material, because the PLA bottles and the PLA short product life cycle or the biopolymer, they are being mixed with the recyclable material, and that can they can pollute and they can make problem during recycling, and also not even in the biodegradation of the material. So we need to have a coherent waste management strategy and develop the more durable product. In Pakistan perspective, we have lots of things available around us, but we need to gel them together, because we have an environmental awareness nowadays. We can have a smog issue, we can have a different type of pollution issue around different cities of Pakistan. So this is one of the best time that we can exploit this environmental awareness. We need the government support is there. The government is willing to support these kind of initiative. There is R&D efforts is going on. We have the industries which can offer their partnership to that one. There are potential applications for these kind of applications. So, and we have the market intelligence, because there is a huge gap in the market to inject these kind of product and to exploit the market for based on consumer demand. So very good perspective in terms of the Pakistan biocomposite technology market. But in order to upscale this one, we need to improve our R&D efforts more. We need to do some sort of pilot scale production product infrastructure and facilities to improve. We need to have this supply chain more sustainable and more integrating. We need to do the process customization, quality control, regulatory compliance, and using the local sources with coordination and networking. So these kind of conferences and these kind of initiative will definitely help in mainstreaming these green composite for circular economy. To uptake the required, we need to have enhanced the performance of the product to improve the socio-economic development and improve the innovation of the product as well. So the expected outcome impact will be use of local resources. We will have a reduce the waste and pollution, and then growing demands for sustainable material. And we will also mitigate the climate change in job. This will definitely improve the job market as well, because it will export potential. This has export potential and some sort of innovation strategy. So we are doing some other projects with the Pakistan Science Foundation and School of Polymer Engineering, Sichuan University, Chengdu, China, on the ultra-high molecular weight polyethylene with rigid reinforced structure for the use in artificial application, joint applications. So we are working on that one. This is a very good project is going on. It's almost near to finish. Another project I did with the Ahmed Saeed and Co. material, for the industrial partner based in Lahore, and they were looking some sort of to develop the master batches for the sanitary applications. So we developed this one on the incorporation of nanoclay in high density polyethylene and calcium carbonate composite for the enhancement in mechanical and thermal properties for construction industry, and that is published and that is developed, and nowadays they are using that products. We done another project with the AP Police in terms of to develop the composite body armors with the slightly slow and lightweight body armor. We done with some work in the Caterpillar to analyze their exhaust valve failure, early failure with the heavy duty natural gas power engine. Nowadays, we are working with one of the strategic organization of Pakistan, the high growth thermal analysis of the advanced composite material. So we develop and design our own chamber, the high growth thermal chamber for that one. That is been going on. We are working in one of the other projects that recycling of the PV module and extraction of the material, because in the near future there will be two problems associated with the PV module. One will be the reliability of the PV module, and second will be the recycling of the PV module. So we are looking to take up this now, and hopefully with that time it will be because we are expecting a huge waste in terms of the PV module, the way it's been manufactured and production is going on, and the way the people are just using this one. So there will be one of the challenge in the future to how we can recycle. So we are looking and we are taking this one as well. we are looking for the future upscaling. We need to, this is my suggestion, that we need to develop a center of biocomposite with the university consortium to improve the R&D efforts and make ourselves in a global standing with the networking, process development, and local utilization of local resources. So this is my proposal. We are open to work with the NTU. And we are looking forward, if there's any kind of opportunity, any kind of working we can project we can initiate to address this issue. So that will be one of the advantage for both and there will be a win-win situation for the economy and for the national level as well. Once again, let me acknowledge my team. I'm my research collaborator within the department and different university, UET Lahore and UET, the process and polymer engineering department, my mechanical department, my MSc student, and my PhD student. So we are thankful to them. And once again, thank you, NTU, thank you to ICPC for inviting me, and hope it touch some of the narrow channels of the mind that the people can think about this product as well. Thank you once again.
Thank you. Thank you very much, Professor Dr. Abdul Shakur, for valuable talk related to the biopolymers. So the house is open. If anyone wants to ask any question, he can ask in the question answer session. He can put up there, or he can ask by raising his hand. Meanwhile, I have a small question from Professor Dr. Abdul Shakur. Normally, when we want to mix the fillers, just like talc or any other type of fillers in the PLA or any other mattress or resin, major issue we face is the viscosity. How we can overcome that issues, or how one can ensure the homogeneous mixing of fillers in our composite?
A very good question and a very challenging top area of what we see. There are, because the talc has a skeletal like this, the structure. And because of that one, when we are looking to mix these kind of issue, there are different types. Like, I don't know which type of mixing you are talking, but what the procedure we are using, we are talking about the mill blending of the material. So in terms of the mill blending, the just like the rotor speeds and the timing and the temperature. So on the other hand, if we improve the temperature in the process, that has a problem for the biopolymer. And because this is if you increase 2% or 2 degree or 3 degree even the temperature, that can affect the temperature of the process or the properties of the material. So that is where the challenge lies for the biopolymer, that it has to be optimized in such a way that it not damage the inherent properties of the polymer, and it can properly ensure the homogeneous mixing of the material. Let me assure that by using the mill blending process and the parameter we are being used, we check this using the microscopy of the just like the microstructure examination, by using the backscattered SEM and even the FACSIM. It was ensured that all the properties and all the particle has been mixed, and it was homogeneously mixed properly as well. There was another issue. You can also use the stearic acid, coat the stearic acid of the talc particle, and that can also improve the mixing and the flow properties of the material. I hope that might answer your.
Thank you. Thank you, Dr. Bashur. There is another question to the participants. How we can ensure the aging of composites by using the biopolymers?
That's one of the, because in order to develop or to upscale this kind of to make this mainstreaming, the issue of this one is because of this aging issue and because of this durability issue, the biocomposite and even generally the biopolymer are limited to the short product life cycle, for just like agricultural mulching film using for certain time and then leave it and then just discard it. The packaging, the disposable application like the glass, disposable glass and plates and all these kind of things. So in order to improve this one, we need to improve the technical enhancement of this material, like to make it more durable material in terms of the mechanical profile and for long standing. But the other issue will become in order if you make this material more mechanically strong and then bring it to the mainstream application, that will definitely improve the economic ability of how this material can be affordable. So that is another challenge we can have with the mechanical challenge, the mechanical profile, or just like the technical profile comes with the economic profile. And because of that one, this material still have lack of confidence or lack of initiation into use into commercial range. And that is where we need to enter and to exploit this issue and to make it more durable for the future generation.
Okay, thank you. If anyone have any other question, he can send us and we will definitely share with Dr. Abdul Shakur. So now we would like to move on to our next speaker.
Excuse me, doctor. Can I leave because I have another meeting? If you want me to stay here, so I will. Otherwise, I can go for another meeting.
No issue. You can leave if you want.
Okay. Thank you so much again, and hopefully we will get in touch. Thank you.
Inshallah. Thank you.
Thank you.
Now I would like to invite Ms. Ayson from YKK Turkey to present his work on study on novel surface treatment of plating for sustainable fashion accessories. So Ms. Ayson, can you hear me?
Hello, yes, I can hear you.
Please share your presentation.
Can you see my screen?
Yes, we can see. You can start your presentation now.
Okay, thank you. Good morning from Turkey. It's a pleasure for me to be here with you. My name is Aysun. I am a chemist and R&D specialist in YKK Turkey. We have an academic partnership with Marmara University. Today's presentation content is textile application, which are the second most polluting sector in the world. I will try to emphasize that textile is not only a fashion, also a very deep R&D subject. We call fashion the output of many chemical processes, especially plastic, metal, and fiber. We are the most important representative of fashion and accessories in the world. Our main content today is sustainable production method in textile accessories. I would like to start my presentation by giving information about YKK. YKK's founder is Tadao Yoshida. YKK was founded in Japan in 1934. One of the most important philosophy of YKK since it's established is sustainability. This thinking is referred to as the cycle of goodness and has always served as the foundation of our business activities. We have inherited this way of thinking from Tadao Yoshida and have established it as the YKK philosophy. Based on this philosophy, sustainability has always been very important to us. The technology developed in Kurobe is spread all over the world. With its continuous self-development and renewal, it has made it a group operating with covering Europe, the Middle East, America, and Africa. We now have operations in 72 countries, 108 companies, and over 46,000 employees. YKK Turkey is the biggest fastening factory between America and Asia. YKK Turkey is just one of the 3 R&D centers in YKK. The fastening business is one core of YKK group operation. slide fastener, snap and button, textile and plastic products are YKK fastening products. YKK fastening products in Turkey are offered jeans, non-denim, leather, bag, luggage, home textile, furniture, baby wear, etc. And among these products range, there are many types of products are sustainable. The products you see here are sustainable products developed by YKK Turkey R&D team with scientific foundations. Being a leader comes with some responsibilities. The impact of textile and fashion products on the environment is huge, and these industries are known as the one of the most polluting industry in the world. As you know, textile and clothing industries, water, energy, and chemical consumption are so much. It is also important to note that around 1% of the clothing materials produced only recycled completely towards sustainable production. We are proud to announce that YKK has formulated the YKK Group Environmental Vision 2050 towards a brighter future for nature and humanity in response to the great need for environmental action on a global scale. Our vision may seem very long-term. This is the environmental vision of entire YKK group, and we are planning to manage as soon as possible with our all efforts. After talking about YKK's environmental friendly approach, I would like to tell you generally about the operation of a button. This slide generally shows the stage a button goes through until the end user. Our first stage is design the button. Mold designs required for working the product are also made here. The next stage is manufacturing and shaping the button components. After this stage, the components enter the plating process. The plated product is taken into a final form by assembly process according to the requirements and sent to the customer. As you can see in this process, we have an electrochemical process for surface treatments. Therefore, I want to share information about plating process in general. In order to extend the economic and useful life of metal materials, their surface must be protected. Corrosion, which starts at a single point on the surface, progresses to the inner parts of the metal over time and rusting occurs. Various surface protection methods have been developed to increase the corrosion resistance of metals and to obtain a decorative appearance. There are 4 types of plating methods commonly used. As you can see below, the first of these, the hot dipping plating method. It is a plating process by dipping the metal to be coated in a molten bed of another metal. The second is the spray plating method. The plating metal is ground into powder, melted with a heat source and sprayed on the base metal to form the plating. Another method is shardizing plating. The powdered coating metal and the base metal are placed in the same case and kept at high temperature for a while. Final one is electroplating method. This is our main method that we use in our products. I would like to explain it more detail to my next slide. As YKK Turkey, we use electroplating method for metal accessories. The basis of electroplating is electrolysis. Electrolysis is the process of separating electrochemical compounds dissolved in a liquid with help of electric current. The coating is done in a suitable electrolyte with the base metal as the cathode and the coating metal as the anode. During this process, the coating metal covers the base metal and protect it from the corrosion. The reason for coating metals include the desire to protect and even improve their physical and chemical properties and appearance. Besides the advantages of the electrochemical plating method, it also has environmental disadvantages. If I were to mention this negatively, use of heavy metal and dangerous chemicals, use of large amounts of water for the process, heavy metal waste mud during the process, it can be summarized like that. In response to these negatives of traditional process, I would like to introduce you YKK's method that contributes to sustainability. In the previous slide, I mentioned YKK's sustainable philosophy. Acrylating technology is part of the effort to achieve this vision across 4 of thema. They are climates, resource, water, and chemicals. Acrylating technology is a new technology that removes 100% of cyanide, chromium, selenium, and other toxic substances without using any traditional plating chemicals. Acrylating offers a number of advantages such as 90% less waste sludge, 60% less electricity consumption, 67% less chemical consumption, 88% less greenhouse gas emission, 65% less water use, 100% less thermal energy use, 100% non-toxic waste as compared to conventional finishing method. In this slide, there is YKK Turkey's sustainable handbook. You can access our handbook and information about our products on our website. And we are fully open any kind of scientific project proposals. That's all from my side. You can find my email address here. Please, for your question, write an email to me. I will be looking forward to your questions. And thank you for your attention and your time.
Thank you, Ms. Aysun. And now we will take some questions. If anybody have any questions, please ask them in Q&A or chat session. Or if somebody have any question, they can raise hand and we can ask them directly. I think we don't have any more questions for Ms. Aysun, who is working in YKK Turkey, and her work was on developing surface treatment for electroplating, and mostly she focused on the developing techniques for electroplating, especially for buttons. Thank you, Ms. Thank you so much for joining us.
Thank you.
And presentation. And now we will move to the next speaker, Mr. Hassan Ubaid Abdullah Al-Faqih from UTM, University Technology, Malaysia, who will present his topic on nanocellular-based composites or flexible functional energy storage devices, challenges and future perspectives. We would like to invite Dr. Hassan Ubaid.
Thank you. Can you see my slide?
Yes, sir, we can see your slide.
Okay, thank you so much. Just allow me a moment, please. Okay, first of all, hello everybody. Thank you to the organizers of this wonderful conference for having me and accepting our abstract. So today I will be briefing you to my review paper, which is on nanocellular-based composites for flexible functional energy storage devices, challenges and future perspectives. Once again, I'm really happy and elated to be part of this third international conference on polymers and composites ICPS 2023. So let me briefly introduce you to the authors of this manuscript. Firstly, here's me. I'm Ghassan Ober Abdullah Al-Faqih, a third-year chemical engineering student at UTM. And my co-author and supervisor is Dr. Rushdi Ahmed Elias, who is a senior lecturer at our university. Also, he's a fellow of IAAM, Sweden, and also a fellow of ISTS, Japan. So let me first of all, talk about the problem statement that ignited and motivated us to write this review paper. So actually, the increasing demand for advanced energy storage solutions is a significant challenge. Also, the necessity to explore sustainable and high-performance nanomaterials. Conventional energy storage technologies have limitations in environmental impacts and efficiency. And lastly, the pressing need for innovative solutions to address these challenges. And our main goal is to contribute to the realization of the Battery of Things era. So, to address this problem statement, we have come with this review paper. So I've summarized everything about our proposed solution in our content of our main content of the paper, which starts with the properties of nanocellulose and the preparation and structural engineering of nanocellulose-based composites, nanocellulose as energy absorption in polymeric composite materials, applications of nanocellulose-derived materials as electrolytes in various energy storage devices. Also, the applications of nanocellulose-derived materials as separators or electrolytes in energy storage devices. Lastly, the challenges and future outlooks facing nanocellulose as an energy storage replacement to conventional materials. So, firstly, let me touch a bit on the properties of nanocellulose. Here are the main 4 characteristics of nanocellulose, as it has high strength and stiffness, large surface area, biodegradability and sustainability. This is the main one that sets it apart from conventional on synthesis composites. And lastly, it has excellent barrier properties. Okay. So let me start with the preparation and structural engineering of nanocellulose-based composites. These are the main 3 strategies utilized in the formation of nanocellulose-based composites. So starting with in-suit strategies, as they involve the formation of nanocellulose within the composite materials during its synthesis. The main advantage is a seamless integration of nanocellulose into the composite structure. It also enables precise control over the composite's properties. Lastly, it ensures homogeneous distribution of nanocellulose throughout the composite. Secondly, the X-suit, which is the exact opposite of in-suit strategies. The main advantages are that it offers flexibility in adjusting nanocellulose properties before composite synthesis. And also it allows for the use of various types of nanocellulose. So this is what sets apart X-suit strategies from in-suit strategies. And lastly, interface structural designs, and from the name, they focus on tailoring the interface between nanocellulose and the other components in the composite. Main advantages are that they enhance the compatibility between nanocellulose and matrix materials and optimize mechanical and chemical interactions within the composites. Further explanations will be provided in the next few slides, so please bear with me. So now, let me touch a bit on the nanocellulose as energy absorbent in polymeric composites. So here are the main characteristics of this subsection. So firstly, the energy absorption mechanism as nanocellulose high surface area facilitates effective interactions with energy sources. Take an example, the absorption of ions or molecules into nanocellulose surfaces in composite materials. Also, the enhanced mechanical properties Nanocellulose reinforces polymeric composites, imparting superior strength and stiffness. Its ideal structural components in energy storage systems, ensuring durability. So also Tyrolean composite properties. The flexibility of nanocellulose sets it apart as a versatile in adjusting nanocellulose properties for specific energy absorption equipments and customization. It's easy to customize and the composites for different energy storage applications. Take supercapacitors and batteries in various types as an example. So now let's move to the sustainable impacts aspects. As nanocellulose is eco-friendly solution, capitalizes on renewable and biodegradable nature. Its environmental impacts as it mitigates the ecological footprints in energy storage technologies. Future implications, innovation potential, as nanocellulose role in energy absorption opens avenues for groundbreaking advancements. Integration anticipated contributions to the engineering of battery of things era. Now, let's move to the applications of nanocellulose derived materials as electrodes in various energy storage devices. I've come up with the four main energy storage devices that nanocellulose can be utilized in. Starting with nanocellulose derived supercapacitors, and secondly, the nanocellulose derived lithium ion battery electrodes, and nanocellulose derived lithium sulfur battery electrodes, and lastly, nanocellulose derived other alkali metal ion batteries. So the first one, nanocellulose has high surface area, as mentioned in the previous slide, and conductivity makes it ideal for supercapacitors. And its ability to withstand the rapid charge and discharge cycle, it enhances the efficiency of the energy storage devices that the nanocellulose is integrated into. And for the nanocellulose lithium ion battery electrodes, nanocellulose enhances the stability and capacity of lithium ion batteries specifically, and it improves the energy density and prolong the battery life. So, moving on to the derived lithium sulfur battery electrodes, nanocellulose mitigates the challenges in lithium sulfur batteries, offering increased conductivity and structural support. It mainly provides the same effects to the sulfur battery electrodes to that of the lithium ion battery electrodes. And lastly, the nanocellulose derived from other alkali metal ion batteries. Nanocellulose extends its applicability to batteries using alkali metal ions like sodium and potassium. It also enhances the performance and offers a sustainable solution for various battery chemistries. Now let's talk about the potential of nanocellulose-based carbon current collectors. Nanocellulose-based carbon current collectors exhibit excellent conductivity, and the integration enhances the overall performance and efficiency of the energy storage devices. As this photo depicts what I just have mentioned, as the nanocellulose higher surface area allows for more interactions per unit mass, leading to higher electrical conductivity and longer conductivity. Longer life cycle of the battery. Also, the competitive advantage of nanocellulose derived electrode materials, leveraging the renewable and biodegradable nature of nanocellulose, mechanical strength as it reinforces electrodes, ensuring durability and longevity. Customization, it's easy and simple to tailor the properties of specific energy storage requirements when they are integrated with nanocellulose. Now let's move to the second last part of our review paper, which is applications of nanocellulose derived materials as separators or electrolytes in energy storage devices. So firstly, let's talk about separators. porous architecture, nanocellulose inherently porous structure serves as an efficient separator, allowing for unbonded ion transport between electrons. Electrical isolation, as it prevents electrical contact between positive and negative electrodes, enhancing safety and reducing the risk of short circuits. The main applications of this type of separators, it's widely applicable in lithium-ion batteries, supercapacitors, and other energy storage systems. So it's approximately like applicable for all energy storage system. And now let's move to the nanocellulose-derived electrolytes. As its main advantage is the conductivity advantage, as nanocellulose inherent conductivity facilitate ion mobility with the electrolyte. Ion transport ensures rapid and efficient transport between ions and electrons, leading to improved overall energy storage device performance and also battery life longevity. Versatility, as it's suitable for use in various battery chemistries, contributing to advancements in lithium-ion batteries, lithium-sulfur batteries, and beyond that. Okay, now let me also re-emphasize that the ease of tailoring properties for specific applications. Thanks to the use of automation capabilities, nanocellulose allows for precise tuning for properties to meet the specific demands of different energy storage technologies. Versatility in design, it enables a creation of separators and electrolytes tailored for specific electrochemical systems and also optimize performance parameters such as ion conductivity and mechanical strength. Lastly, let me talk about the challenges and future prospects. The main challenge that nanocellulose integration in energy storage devices faces is the integration complexity, as achieving seamless integration of nanocellulose into energy storage devices may pose challenges due to its unique structural characteristics compared to the composites incorporated with. Also, processing methods, developing scalable and cost-effective processing methods for large-scale production remains a hurdle. This is because nanocellulose utilization in the energy storage devices is a new thing in our current time, and there haven't been any production of methods or like industries that could utilize or use or produce massive amounts of nanocellulose which can be used in the industry. Compatibility, as like ensuring compatibility within the existing technologies and materials within the energy storage system. This is also another challenge that nanocellulose face at the moment. Now let me talk about the future prospects. As enhanced energy storage performance, continued innovation in nanocellulose applications promises to enhance the performance matrix of energy storage devices, and also emerging battery technologies. Nanocellulose role in the next generation battery technologies, such as solid-state batteries, presents existing prospects. Commercialization opportunities, as challenges are addressed, the commercialization of nanocellulose-based energy storage solutions will likely gain momentum. The nanocellulose, utilization in the energy storage devices is kind of a hot subject in these 2 years, as it has a lot of potential to unlock. I think that's it from me. Let me re-emphasize that our main focus for this report, for this paper, is to emphasize the use of sustainable and renewable resources in our energy production and energy use. And here are the references to all my pre-mentioned points. And thank you all for listening. If you have any questions, feel free to ask. Thank you so much.
Thank you, Mr. Rassan. I would like to ask one question, that what will be the effect on the battery life for this nanocellulose compared to the conventional materials of electrodes, separators, and electrolytes? So what we will see in the battery life point of view?
Okay, thank you so much for the question. Actually, the main effects that we would see in the battery life is its longevity, as like many current batteries faces like lack of the battery life degrades after some times because they have some limitations in the charge discharge ability. Thing is it increases the charging time. Sorry, it decreases the charging time, meaning the new batteries with the nanocellulose utilized will charge like maybe faster. And the main and biggest advantage is that this is a green resource, and our Mother Earth has suffered enough from conventional materials and such things. I hope I addressed your question correctly, Mr.
Now you have cleared my point that these nanocellulose materials are even more advantageous than the conventional materials because they have, as you have mentioned, their increased charging time, which will definitely lead to, you can say, more time to go for beneficial work. And these are green resources. So thank you so much for your very innovative work on nanocellulose-based composites for flexible function and energy storage devices. And you have very well established the literature review and you have produced a review paper on it. Thank you so much. If anybody else have any question, they can ask or raise hand. I think we don't have any more questions. Thank you so much. Thank you so much, Rasan Obed, for your presentation on this novel topic. Thank you so much.
Thank you. Thank you so much. And I would like to thank you, our esteemed speakers and organizations, again for having us. And thank you so much.
And now we would like to invite Dr. Lau Yu Sean from University Technology Malaysia, UTM, on the topic of innovative magnetic cellulose materials for environmental and industrial applications. And a comprehensive review will be given by Dr. Lau.
All right. Can you see my screen?
Yes, we can see.
All right, so good day, everyone. I'm Lau Yishan, chemical engineering student in my third year. I'm from University Technology Malaysia, and it is my pleasure to share my explorations of innovative magnetic cellulose material for environmental and industrial applications. So this comprehensive review was a collaborative effort with my esteemed lecturer, Dr. Ilyas, from the Department of Chemical and Energy Engineering at University Technology Malaysia. Detailed journey through our findings, shedding lights on the promising potential of magnetic nanocellulose. So let's delve into the intricacy of this transformative material. As we embark on this scientific journey, let's first address a critical issue, the escalating threats of environmental pollution. Traditional pollution control methods are facing limitation in effectively managing the increasing complexity of pollutants. This challenge, coupled with the global call for sustainable practice, has spurred our investigation into alternative material that can minimize environmental impact. Our research served as a response to this urgent need for innovative solutions. In recent years, the convergence of nanotechnology and cellulose science has led to a groundbreaking advancement in the development of magnetic nanocellulose material. Our review provides an overview of key studies conducted by leading researchers, highlighting the transformative potential of magnetic nanocellulose in various environmental and industrial applications. Now, let's understand the foundation of our exploration, nanocellulose. This versatile nanomaterial derived from cellulose fiber exhibits its unique properties such as high surface area, mechanical strength, and biodegradability. We will explore three main types: the cellulose nanofiber CNFs, cellulose nanocrystal CNC, and bacterial nanocellulose BNC, each with distinct characteristics and application. So as we explore the vast application of nanocellulose, its remarkable versatility comes to the forefront. Our magnetic nanocellulose, a product of innovative research, shows crucial application in various fields. Notably, it demonstrates exceptional biocompatibility, paving it fast for advancement in biomedical science, drug development, and tissue engineering. Furthermore, it showcases its role in creating advanced material, reinforcing composite for heightened mechanical properties with potential implication in diverse industries. Additionally, our material emerged as a sustainable alternative to synthetic material, contributing to the reduction of environmental impact. Also, the synthesis of magnetic cellulose (MC) is a pivotal aspect of our research. Iron precursors undergo hydrolysis in an aqueous cellulose nanofiber dispersion, leading to the controlled formations of the magnetic cellulose. The resulting thin, flexible films, prepared through the meticulous hot press process, creates a composite material with magnetic and cellulose components. This synthesis lays the foundations for the unique properties of our magnetic nanocellulose. Next, understanding the structural intricacy of our material is also very crucial. Temperature-dependent surface roughness, as revealed by our analysis, exhibits dynamic change correlated to the enhancement of MC conductivity. Theoretical models such as percolation theory provide insight into the conductivity, showcasing an alignment with experimental results. Next, I will present about the porous structure and superorophilic coating. At the heart of our magnetic nanocellulose efficiency lies its unique structure. So visualize tiny beads with numerous pores and a coating with a strong affinity for oils. These pores and the coating work synergistically to swiftly capture oils and other substances. The coating will act like a magnet for oil, ensuring effective adhesion to the beads. This collaborative mechanism enables our material to efficiently capture and remove pollutants, making it a valuable asset for environmental cleanup. Next is capillary force and swirling effect. Let's delve into how our magnetic nanocellulose sees pollutants, envisions the beads employing the subtle force, akin to gentle fingers, to draw in oils and other complex substances. This force will facilitate the rapid infiltrations of oils into the beads. Additionally, the beads possess an absorbing ability. They swirl when saturated with oil. This unique swirling effect will enhance their capability to absorb a significant amount. The dynamic interplay of this force and the swirling effect positions our material as an exceptional choice for addressing the environmental challenge. And the last mechanism is the magnetic responsiveness. Now let's discuss about the magnet. We integrate the minuscule magnetic component into our beads, rendering them responsive to magnetic fields. This responsiveness allows easy manipulations and collections of the beads using the magnet. Imagine using a magnet to selectively extract oil-filled beads from the water. This magnetic feature not only enhances the cleanup efficiency, but also enables the reuse of the material. Hence, it not only proved effective, but aligns seamlessly with the principle of environmental sustainability. As we venture into application, one of the key areas is dye removal. The intricate interplay of magnetic nanocellulose with dyes influence its ability to absorb, with factors like temperature dependence and synergistic enhancement playing the crucial role. Our finding contributes to the evolving landscape of efficient dye removal technology. Moving forward, our exploration extends to the critical domain of oil removal. The porous structure, coupled with a super oleophilic coating, proved instrumental in effectively absorbing oil and organic compounds. The magnetic responsiveness of our nanocellulose material facilitates the selective removals of oils, presenting a promising avenue for effective and sustainable oil spill mitigation. And the next one is about organic solvent. Diving deeper into the application, the compatibility of magnetic nanocellulose with the organic solvent will become the evidence. Its multifaceted approach influenced by factors like temperature dependence and the synergies removal achieved through the integrations of magnetic nanoparticles positions our material is also a key player in addressing the challenge associated with the organic solvent contaminations. So the next one is the potential applications. As we contemplate the vast potential of magnetic nanocellulose, diverse application will emerge. From biomedical application and smart material to an innovation in electronics and water treatment, our material transcend the traditional boundaries. This convergence of nanotechnology and cellulose science open a new frontiers for sustainable solutions in various domains. However, no scientific exploration is without its challenge. Scalability stands as a primary hurdle, demanding refining for reproducibility and cost effectiveness on a larger scale. The environmental consideration of production process emphasize the needs for green and scalable methodology. Despite this challenge, the multifunctionality of magnetic nanocellulose opens avenues across the diverse domain. It holds promise in catalyst, water purification, oil spill mitigation, and advanced oxidation process for pollutants removal. In conclusion, our journey into the realms of magnetic nanocellulose unveils a promising material with the potential to revolutionize environmental and industrial application, significantly improving the absorptions and recyclability of nanocellulose. Our research contributes to the evolving landscape for material science. These challenges we face are not roadblocks, but stepping stone for future innovation. As we collectively pave the way for advancement in material science, we will find a way out. That is all for me. Thank you for your attention.
Thank you, Ms. Lau. I would like to ask one question. It's about the dye removal. So when we face problem in water, can you hear me?
Sorry, can you repeat the question? I can't hear you clearly,
I
sorry.
would like to ask the question about dye removal. That once it is absorbed to the magnetic field,
Dye remover, sorry, I can only hear dye remover.
once it is absorbed to the magnetic cellulose. So when we try to regenerate our magnetic cellulose, so the process will be chemical or mechanical to regenerate our magnetic cellulose back.
All right, thank you for your question. So I think that in my opinion, I think that it could be the integration of both chemical and mechanical to make the strength of the magnetic nanocellulose to be better. And in this way, we will also combine both these strength to make the dye removal process to be more effective, because when our strength of our magnetic nanocellulose is better, the strength of remove the dye will be better also.
Okay. So I would like to ask one more question relating this. If we are using
All right.
chemical treatment, so will it be sustainable or will it lead to unsustainable development if we are using it to increase the efficiency of dye removal? As you have suggested, there will be integration of chemical and mechanical treatment. So the process will be sustainable or not sustainable?
In my opinion, thank you for your question. In my opinion, I think that it would be more sustainable because we will need the strain, the integration for marine aspect, and then in this case, the process would be more sustainable in terms of its efficiency.
Okay, thank you so much. And you are working on a very innovative approach to uh, for sustainable future. And I thank you. I would like to thank you for your participation. Thank you so much for joining us.
All right, thank you so much.
Okay. Now we will conclude this session by expressing our gratitude to our speakers for their time and dedication in delivering a remarkable session. The information presented was incredibly thought-provoking, and I hope it generates ideas for further exploration. Now there will be a break for almost 1 hour for lunch and prayer. We will start again for our next session at 2 p.m. Pakistan Standard Time. So please be with us. Thank you.